Hi everybody. In this section we're going to start making the transition from some of the more technical aspects of things that we've covered in order to prepare you for your program work to more general algebra and geometry kind of topics. So we're going to spend one lesson here working with percents and percent applications so that when you stumble across those you've got a good strategy for working with those type of problems. When we're done here you'll be able to identify the amount, base, and rate in any percent application and have at least one practical way to find whichever missing value you're trying to look for. So let's take a look. Okay, so first thing that we need to do is review what a proportion is. A proportion is basically an equation that relates to ratios. Here's a simple example of this. Suppose that 3 cars out of 20 have tires that are underinflated. So that gives us a ratio of 3 low tires out of every 20 cars. So then how many cars out of 255 in the parking lot are going to be underinflated? Well, we assume that that ratio would also hold for the entire parking lot. So since we're told that the whole lot has 255 cars, then what we're trying to find is what is this number in the top right? How many low tires would we have in the whole lot? If we write that without units, we could just say 3 over 20 should be the same as x, our unknown, over 255. Now, this is one of those things that people tend to remember, and maybe you do too. Do you know how to solve a proportion like this one? Well, I'll bet you have heard of cross multiplying before, and so a quick review here of that. One property of a proportion is that the diagonal products, or the cross products, have to be equal. So the diagonal product in this direction, which is 20x, has to be equal to the diagonal product in the other direction, which is 3 times 255. Or if we carry out that multiplication, we get 20x is equal to 765. And then to solve for our unknown x, we'd simply divide both sides by 20. And when we do that, x turns out to be 38.25, but it's unlikely to have a quarter of a low tire, and so we would probably say that there are 38 vehicles with low tires in the lot. Now, we did that because we're going to use proportions to solve percent problems. Let's see how to do that. Okay, let's talk about base rate and amount for just a minute here. The base rate and amount are the 3 parts that are going to be included in any place you see a percent applied. So let's look at a simple case. Suppose you had 1 out of 4 trucks in a particular fleet that were overdue for their oil change. I think you'd agree that you could just say that that one truck is 25% of 4, or that 25% of this fleet was overdue. Now, let's dig into that a little bit deeper. The base would be the whole fleet. So in other words, all 4 trucks. The base is the full amount that we can talk about, and the base always represents 100%. And because of the way that we use the English language, the base usually shows up next to the word of. So whenever you picture the base in your head, think about whatever the whole thing is, or the starting value of what we're working with. The second part is called the rate, and the rate is easy to spot because that's your percentage value. Here we're saying that we've got 25% of the trucks that are overdue for their oil change. That's our rate, 25%. Now that rate is worth something, and in fact 25% of the fleet is 1 truck. So that's what we call our amount. The amount is always what the rate is worth. And because of the way we use the English language, the amount almost always shows up next to the word is. 1 truck is 25% of the whole fleet. And the thing to note here is that the amount is typically some portion or some part of the whole thing or of the base. Here's why that's important. Since the word percent means per hundred, percent literally means per 100, then we can set up any percent problem using a proportion. And so here's our relationship right here that we're after. The rate over 100% is always the same as the amount divided by the base. We get a proportion there, and as long as we can find 2 of these values, we can solve for the third one. So here's a simple example. How much tax, if we assume 5.5%, would we have to add to the price of an LCD TV that sells for $747.99? Well, let's note here, first of all, that we can easily identify the rate. The rate is our percentage, and in this case, that is 5.5%. The base would be the regular price of this TV, the whole thing, and so our base in this problem is going to be $747.99. And what we're trying to find is the amount, that is to say the amount of tax that will get added on. So let's fill these values into our proportion. We would say that the rate of 5.5% out of every 100, or in other words, we'll have to pay $5.50 out of every 100 we spend. So then we'll leave our variable as being A here, the amount, over $747.99. How much tax will we have to pay if we're spending $747.99? There it is. Now solving that is easy. We'll cross multiply. In this direction, we get 100A. In the other direction, 5.5 times 747.99, we get 4,113.945. Now we're going to divide both of those by 100, and the amount of tax that we're talking about here turns out to be $41.14. And that settles the issue. We're going to owe about $41.14 in tax. So the proportion that we have right here, this is one of two main strategies you can use for solving percent problems. Let's solve that problem one more time, but let's take a slightly different approach. Notice that when we solved this problem, we left the percentage just as it was. We put 5.5 over 100. We did not have to move the decimal. As you probably remember from math classes you've had before, we can change those percentages into decimals by moving the decimal point 2 places to the left, which is the same as dividing by 100. And so our second way to solve this is using this relationship on the right. If we put the percentage or our rate as a decimal, then we can plug that into this wheel and solve for the third one as long as we know the other two. So let's solve this problem again. How much tax would we have to add on to that TV if we buy it for $747.99 at 5.5%? Well, this time we're going to say that our rate is 5.5%, but we're going to treat it in decimal form, so 0.055. Our base is still $747.99. And the way we use this wheel is if we're trying to find the amount, we cover that up, and the base and rate are next to each other, which means these two things should get multiplied together. So what this wheel tells us is that the amount is equal to the base times the rate. And so the amount of tax would simply be $747.99 times our rate, but this has to be in decimal form for this method, 0.055. And if you do that on your calculator, it won't be any surprise at all that we get $41.14. So we didn't need a proportion there. We used this relationship where we did the decimal move instead of relying on the proportion to do it for us. We're going to look at a number of applications here, and we'll use both methods a few more times, and you can use whatever method you prefer. Okay, I'd like you to take a shot at this one. The typical person needs 2,000 calories per day for normal activities. So what percentage of your day's calories are you getting if you have a Whopper with fries and a Coke, and those calorie values are given there? Take a minute, do that, and unpause when you're ready to see that solution. All right, well, first of all, we have to figure out how many total calories we've got there, and we have 1,320 if we add up the calories from the Whopper, the fries, and the Coke. And so then the question is, well, what are our base and our rate and our amount? The question itself asks what percentage, so that tells us that we are trying to find the rate. That leaves us with the amount and the base. The 1,320 is not the full amount that we need for the day, so that must be our amount. And the base would be the full amount that we need. That would be the 2,000 calories. And so if we use a proportion for this, we would say that our rate over 100% is equal to our amount, 1,320, divided by the base, which is 2,000. I'll leave it to you to take your calculator and multiply 1,320 by 100 and divide it by 2,000. And if you do that, you get 66. Now that's a percentage. If you use the proportion method, you don't have to move any decimal. You're done. You get 66% of the day's calories right there in one meal. If you use the wheel, since we're looking for rate, we would cover that value up. And since A is over B, we would say that rate is amount over the base. And so if the rate is the amount over the base, that means that we're simply going to divide the 1,320 calories we get in this meal by the 2,000 in an entire day. That'll give you 0.66, but remember the wheel always treats the rate as a percentage. You need to recognize then that that is 66%. Of course, we get the same result. So by either of those methods, you should get 66%. Okay, we're going to take a look at a few applications of percent here that relate to some common percent formulas. You can use these formulas, or you can treat these as proportions or use the wheel. We're going to solve each of these a couple of different ways. You can use whatever method makes sense to you. Within the United States, there was about 267 times 10 to the 6th, that'd be million, 267 million active Twitter accounts in April of 2018. By April of 2019, it had actually gone down a little bit. There was 262 million accounts. The question is, what was that percent change? Well, percent change is simply the change in value, in other words, the new value minus the original, divided by the original value. Percent changes in general, if they're positive, it means that our change is increasing. And if it's negative, it means that our change is decreasing. So let's solve this. If we strictly use the formula, that's pretty easy. We can plug in these values. And if we put in our new value of 262 times 10 to the 6th, or million, minus the original value of 267 million, and divide by the original value of 267 million, we can do that without too much trouble. 262 million minus 267 million, note that that's a negative number, so that's negative 5 times 10 to the 6th, or million, divided by 267 times 10 to the 6th. And since we're talking about millions in all these cases, those just cancel off. And so we have negative 5 divided by 267. Now all these input values had 3 significant digits on them. We should keep 3 significant digits, and we get negative 0.0187, and again that's a decimal, so that needs to be turned into a percent, and if we do that we get negative 1.87%. The negative sign is important there because the negative sign tells you that it's decreasing. Positive value would mean that Twitter usage had gone up. Now let's solve that one more time, but let's take a slightly different approach. Okay, if we use the proportion on this, clearly we're asking for percent change, so that tells us that we're trying to find the rate. That'll be our unknown. And as far as our amount and base goes, the base is always the starting value when things are changing, and that's exactly what happens here. So our base should be the starting value, and in this case that is 267 million. Now, if we're trying to find the percent change, the amount should be the amount of the change. It's tempting to put 262 million in there, and you could, but a better approach is to say the amount of the change is the amount in our proportion. And so we already showed that there was a 5 million user decrease in Twitter, so that's negative 5 times 10 to the 6th. Once again, those cancel off, and so the proportion that we need to solve is R over 100 is equal to negative 5 over 267. And if you solve that proportion, you'll get, no surprise, negative 1.87%. Same result we got using the formula. Now you might say, well, those are kind of the exact same thing. And you're right. They're just different ways of thinking about the exact same math. Again, any method that you like is just fine. Okay, let's take a look at what is kind of a tricky problem. There's a box of Hamburger helper here that says 20% more free, and this is a 7.2 ounce box. And so the question is, what was the size of the original box? Well, this is a percent change problem. And so we can use our formula we were just given. Our percent change in this case, we were told that it is 20% more. And since it's an increase, we're going to leave that being positive. Now our new amount, we know what that is. That's 7.2. We'll leave the units of ounces off of here. Our original amount, we don't know what that is. O is a bad variable. It looks like 0, so we're just going to use x here over the original amount of x times 100%. Now if we divide both sides by 100, that basically peels this off the right and turns this into a decimal on the left. So we could say 0.20 is equal to 7.2 minus x over x, and we're going to have to do a little bit of algebra here. Let's multiply both sides by x to get rid of this denominator. 0.20x is equal to 7.2 minus x. Now let's add that x to both sides. And 0.20x plus a whole x is now 1.20x equals 7.2. And the last thing we need to do is divide by 1.20. And x turns out to be exactly 6 ounces. So the original box was 6 ounces. Okay, that works out fine, but you'll notice that there's quite a bit of algebra that we had to do there. Let's take a different approach to this that won't require nearly as much algebra. Okay, let's use a proportion on this problem. First of all, the bases are unknown. That's what we're trying to find because we do not know what the starting value was here. We do know what we ended with. The amount that we had when we were done was 7.2 ounces. Be careful because it's tempting to say 7.2 ounces was your base, but it's not. That's not what we started with, and so it can't be the base. Now the rate. What would our rate be? Well, that 7.2 ounces is all of the original size plus the extra. Our rate is 120% because it is 20% more than it was. Another way to think about that is to say they used to sell this box and we got 100% of a full box. But then they added a little bit more to this box. They added an extra 20%. And so now our 7.2 ounce box is 120% of what it used to be. If we fill those into our proportion, we get 120% over 100%. And that's equal to 7.2 ounces over our base, which we'll call B. And so we could say here that the top value are all of our new amounts for the new box. And the bottom numbers, 100% and the base, that was our original box. Now you could take your calculator, take 7.2 times 100 and divide by 120, but you're going to get, again, no surprise, 6.0 ounces, the same answer we got using the formula a minute ago. So the method you use, that's up to you, but in any case you should get 6 ounces. Problems like this where the base is unknown are tricky. We're going to look at some more of those, but anytime your base is unknown, be very careful about how you choose your rate. Here we had to call it 120% and not just 20% because we were getting 20% more than we originally were. Okay, this is a similar problem. Gas is about $2.59 per gallon, and that's about 10.4% higher than it was last year at this time. So my question is, how much was it last year? Take a minute and see if you can solve that percent change problem and unpause when you're ready to see the solution. Okay, let's use the proportion for this one. We don't know how much gas was last year at this time. That was our starting value, and so here again we don't know the base. That means that our current price of $2.59, that must be our amount, kind of like the 7.2 ounce box was in our last example. That also means that our rate must be 110.4%. That is to say, it represents an increase of 10.4%. And here again, the price of gas last year, that would have been our base, or 100%, but this year it's 10.4% higher for a grand total of 110.4% in our problem. So we have 110.4% over 100%. That's the new price compared to the old price. And that's going to be equal to our amount of 259 over our unknown base, which is again the new price over the old price. I won't show the work here, but you could take your calculator, 259 times 100 divided by 110.4, and you should end up with a base value of $2.35. Okay, I want to look at a couple more problems here that are kind of similar, but I want to shape your thinking a little bit. Percent error is another common application. Percent error gives the amount of error in a measurement relative to what the true value actually is. So our percent error would be the measured value minus the true value. That is to say, that's how far off we are if they're not exactly the same. And our base is always the correct or the true value. So let's solve this problem. A scale is known to have an error of negative 3.50%. So you tell me, is this scale measuring too heavy or too light? Well, if its error is negative, that means it is underreporting the weight, and so it's measuring too light. The object you put on the scale is heavier than what the scale says. That's going to be our percent error. Negative 3.50% is equal to our measured value, that's what the scale reports, 423.8, minus our true value, that's what we're trying to solve, divided by the true value times 100%. Now we can solve that a lot like we did our previous example. We can divide both sides by 100%, and this becomes the decimal, negative 0.035. Equals 423.8 minus t over t. Now we'll multiply both sides by t to get rid of that fraction. That gives us negative 0.035t equals 423.8 minus t. Once again, we're going to add t to both sides. That's like adding one whole t, so be careful when you do that. Negative 0.035t plus one whole t is 0.965t. Equals 423.8, and we're almost there. Now we can just divide to find our answer. T is equal to 423.8 divided by 0.965. And if you do that, the true weight is of course going to be a little heavier, 439.2 if we round off it two significant digits. Technically, though, our percent error only had 3 significant digits, so we really should round this off at 439 grams because we are limited to 3 sig-digs. Now I'm going to solve that one more time quickly using a proportion so that again so you can see both ways, and I want you to make sure that you see a certain relationship here. So once again, rate over 100% is the amount over our base. Our base would be the true value, and once again, we don't know what that is. I'm trying to do a lot of these base problems that are unknown because they are the tricky ones. The amount, we do know what the scale is reporting. The scale says that our amount is 423.8. Now our rate, this is the tricky part. Is the scale reporting the full 100% of the weight? It's not. Our rate would be 96.5% because the scale is reporting 3.5% too low, so it's not reporting the full weight of 100%. If we take the full weight minus the 3.5% that the scale is not reporting, we're left with 96.5%. Visually, what we're saying is we would like a scale that reports all 100%, but it's not reporting 3.5%. That's our error. It's only reporting the other 96.5%. And so if we put those values into our proportion, 96.5% over 100%, That equals the amount of 423.8 divided by our unknown base. And if you take 423.8 times 100 divided by 96.5, you'll end up with, again, 439 grams. Okay, I'd like you to take a minute and do one practice problem. You've got an ohm meter that measures the resistance of a 330 ohm resistor to be 324.5. What is your error in that measurement, assuming that the resistor really is 330 ohms? Go ahead and figure out what your percent error is here. Okay, well, we know that percent error is the measured value minus the true value divided by the true value. We can put on our values. Our measured value is 324.5 minus 330 divided by the true value of 330. That tells us that we are underreporting, or we're failing to report 5.5 ohms out of the 330. Divide those according to our formula and multiply by 100. And you end up with negative, because we are underreporting after all, 1.67% error. And of course, you could use your wheel for this too. The question is, what is the percent error? So we're trying to find the rate, or our percentage. The rate is the amount divided by the base, where the amount is how much we're failing to report, the amount of error. And so as we just saw, our rate will be the amount of error, that's underreporting by 5.5 ohms, compared to our base, the known value of 330 ohms. And if you divide that, we're going to get a decimal value, negative 0.0167, which again with the wheel, that's always a decimal equivalent. That's negative 1.67%, just as we got using the formula. Different approach to what is basically the same arithmetic here. Okay, here's our last problem of the day, percent efficiency. Since you're all in some pretty technical fields, you deal with efficiency pretty often. Percent efficiency is simply the amount of power that we get out of a device relative to the power that we put into it. So we just divide our output power by our input power and multiply by 100, because we'd get a decimal value there. So a good example, this is a portable generator. It's got a 16 horsepower engine, and it only creates 8,500 watts of power. And the question is, what is the percent efficiency of the generator? Okay, well, our percent efficiency there is obviously output power over input power. The output is the electricity that we're getting out, so that's 8,500 watts. That's what we're getting out of this generator. But our input power, the generator is getting 16 horsepower of mechanical power being given to it. So that's our input power. Now we have a problem. We're taking watts and dividing by horsepower. Those units don't cancel at all. If we want to do this division, we have to make these units match. So we either need to change the horsepower into watts or the watts into horsepower. In other words, our dimensional analysis tells us that we're going to get nonsense here. Let's change those 16 horsepower to watts. You have this on your conversion sheet. 16 horsepower over 1 is what we want to convert. Your conversion sheet says 1 horsepower is about equal to, that's an approximate conversion, 746 watts. So 1 horsepower will go on the bottom, 746 watts will go on the top. Those units cancel. And those 16 horsepower are equivalent to 11,936 watts. And so now if we do this computation again, our percent efficiency is the 8,500 watts we're getting out of the electrical generator divided by the 16 horsepower, or equivalent to 11,936 watts that we're putting into it. Now the units cancel, and we're going to get just a pure percentage out of this. And we get 71%. We can only keep 2 sigdigs there because the 8,500 watts only had 2 sigdigs on it. Now once again, I want to take one more look at that in a different way, and that is this. Our rate is what we're trying to find here, since the question is what percentage. over 100 is the amount over our base. So the amount that we're getting out, remember the base is what we started with, and we're starting with 16 horsepower. So we're going to get 8,500 watts out when we started with 16 horsepower. Now here again, these units don't cancel and we need them to. So if we solve this, we get R over 100 equals 8,500 watts over the work we did just a minute ago to show that 16 horsepower is the same as 11,936 watts. Now those units cancel, and if we take 8,500 times 100 divided by 11,936, we get a rate of 71%. So we can use a proportion there, or we could use the wheel, but lots of ways to solve these problems. Make sure as we wrap up this lesson that you're able to perform percent efficiency computations either using the wheel, the proportion, or that formula, as well as percent error calculations. Again, any method you want is fine, but make sure that you're comfortable solving those types of problems. Percent change is another common application that I'll ask you to do when we get to our unit test. And in general, be able to find the amount, the base, and the rate of the problem with one of those techniques. There will be some other percent problems in your practice problems that I give you for this assignment as well. Make sure to reach out if you have any trouble with those. In our next lesson, we're going to start our algebraic topics, and so we'll see you there.